Hi everyone. As we know from the definition, probability assigns a number to every event. That number is denoted by P of E, and its meaning is the likelihood of that event. This number must satisfy certain axioms. The probability of any event should be non-negative, and we also figured out it should be less than 1. The probability of the entire sample space, probability that something happens, is always 1. And if the events are mutually exclusive, if they don't have any overlap, then the probability of their union can be computed by summing their probabilities. This was our definition of probability. How would we compute the probability of the union of two events if they are not mutually exclusive, if they do have some overlap? Imagine we would do the same thing. We would add the probability of E to the probability of F. Would that be the correct answer? No, because we would double count the overlap. The intersection of E and F is included in both E and F. And so by summing these two parts, we counted it twice. So this formula, this naive formula, is wrong because it double counts the intersection. How do we correct that? We subtract one copy of the intersection. Now we don't double count it. We count it just once. That formula is an important principle, and it's called the inclusion-exclusion principle. To prove this principle more formally, break down the union of E and F into 3 mutually exclusive parts: A, B, and C. A is this crescent, and it's E minus F. B is this wedge, and it is E intersection F. And C is this crescent, and it is F minus E. Check that A, B, and C are mutually exclusive. And the left-hand side, E union F, is the union of A, B, and C. Therefore, by the additivity axiom, because A, B, and C are mutually exclusive, is just a sum. In the right-hand side, E is the union of A and B, two mutually exclusive events, and so it's P of A plus P of B. F is the union of B and C, two mutually exclusive events, and so it's P of B plus P of C. And the intersection is just B. Now, if you compare this expression with this expression, you will see that they are the same, and that proves the inclusion-exclusion principle. Here's an exercise. A construction company claims that 97% of the homes it builds are safe, are earthquake safe. 96% are flood safe, and 91% are both earthquake safe and flood safe. Disprove their claim. To do this, formulate this problem probabilistically. We choose a home at random, according to the uniform probability, where any outcome, any home, can be chosen equally likely with the same probability. And let's look at these 3 events. E will be the event that the chosen home is earthquake safe. F will be the event that the chosen home is flood safe. And E intersection F is the event that it is both earthquake and flood safe. And now let's compute the probability of the union, the probability that the chosen home is either earthquake or flood safe, or both. According to the inclusion-exclusion principle that we just proved, we have this formula. The probability of E, the probability of choosing an earthquake-safe home at random, is 0.97, because 97% of the homes are that. The probability of F, flood safe, is 96%, so 0.96. And the probability of both is 91%, minus 0.91. Then we compute that number, and it turns out to be 1.02, which is bigger than 1. And that can never be true. The probability of any event must be bounded by 1. Therefore, the conclusion is false, and that means that the original claim of the construction company is false. So we learned how to compute the probability of the union of two events. If they're mutually exclusive, then we just sum their probabilities. If they're not, we still sum their probabilities, but then correct it by subtracting the probability of their intersection. What about three events? Suppose we have events E, F, and G. How do we compute the probability of their union? We can start in the same way with the naive formula that just sums all their probabilities. Then we realize that that formula double counts the intersections. So we correct that. We subtract a single copy of each intersection that was double counted. Is that the final answer? Not quite. When we subtracted this, and this, we subtracted 3 copies of all 3 Y's intersection, just in this middle part. So what happens to this middle part over here? First, we counted it 3 times, and then we subtracted it 3 times. As a result, we have not counted it even once. And let's correct that. We add 1 copy of the 3 Y's intersection, E, F, and G. That is the inclusion-exclusion principle for 3 events. I guess the pattern is clear to you now. If we have 4 events, for example, we add the probabilities E, F, G, H. Then we subtract the probabilities of all pairwise intersections. Then we add the probabilities of all 3 Y's intersections. And then we subtract the probability of 4 Y's intersections. And that generalizes to 5 events. It becomes just the ever rebalancing game of adding intersections and then subtracting intersections and so on and so forth. Every time we're correcting the previous step. The general inclusion-exclusion principle for any number of events, E1 through En, we first add all the probabilities. Then we realize, oh, but we have double counted the probabilities of their intersection. So we correct that. We subtract 1 copy. And then we add the 3 Y's intersections. And then we subtract the 4 Y's intersections and add the 5 Y's and so on and so forth. At the very last step, we add or subtract the intersection of all of these events. We add or subtract it depending on whether N is even number or odd number. It will be -1 to the power N plus 1. That picks the correct sign for this probability. The sum here is over all unordered pairs of distinct numbers I and J. And here the sum is over all unordered triples of distinct numbers I and J and K, and so on and so forth. How many terms are in the sum? How many ways are there to choose the unordered pair of 2 numbers from N of them? That's N choose 2 terms. And here in the sum, how many triples are there? How many ways are there to choose the unordered triple from N objects? That N choose 3 terms in the sum, and so on and so forth. Let's put our hands on an important problem of probability that illustrates the inclusion-exclusion principle, the matching problem. Imagine that we have N students in a class and we are returning the graded exams to them completely at random. let's find the probability that no student gets their own exam. That situation is called a derangement, the event where no students get their own exam. Do you think it is likely that no student get their own exam or unlikely? Let's find out. Our experiment is to return the n exams to n students. An outcome is just a particular way to return these exams, just to know which student get which exam. The set of all outcomes, the sample space, then, is the set of all ways to return the exams. There are n factorial ways to do that. To see this, imagine I keep the stack of exams, then I shuffle them, so I make some reordering, some permutation of this exams, and after I do this permutation, I return the top exam to student 1, the next second exam, student 2, student 3, and so on and so forth. The number of ways to return the exams is just a number of permutations. It's how many ways I can reshuffle the exams, and that's n factorial, the number of permutations on n objects. We are interested in the probability of a derangement, that no student gets their own exam. It would be simpler to pass to the complement. The complement of a derangement, the complement to the event that no student gets their own exam, is the event that some student gets their own exam, at least one. There are n students, so this event is the union of the events EI, where EI is the event that the particular student, student I, gets their own exam. Remember that the union stands for logical operation OR. At least one student gets their own exam means that the union happens. The probability of this union will be computed using the inclusion-exclusion principle. This formula. To apply it, we'll first need to compute the probabilities of each event EI, as well as their intersections. So let's compute the probability of EI first. All outcomes are equally likely. This is uniform probability, and so it can be computed as a fraction, number of outcomes in EI over the number of outcomes in S. What's the numerator? How many ways are there to return the exams so that this particular student, I, gets their own exam? There are n-1 factorial ways. To see this, imagine I have the n exams. I look for student I, look for students I exam, their own exam. I gave it to her, and then I tell her, go home. There's only one way to do that. Now, once that is done, I am left with n-1 exams, and I still need to return those to n-1 remaining students. How many ways are to do that? There are n-1 factorial ways to do that. And this is n factorial in the bottom here. The factorial is the product of all numbers between 1 and n-1, and this is the product of all numbers between 1 and n, and so this ratio is 1 over n. Next, let's compute the probabilities of the intersections. Now we're fixing two students, I and J, and we're computing the probability of the intersection. Intersection means and. That means that we're looking at the probability that both students, I and J, get their own exams. So it reduces to counting the number of ways to return exams so that two specific students get their own, and that is n-2 factorial ways. To see this, perform the same mental experiment. Imagine I'm holding n exams, and I know that these two students, I and J, must get their own, so I look up their exams first. This is for I, and this is for j, and I send them home. That's only one way to do that. But now I'm left with n-2 exams that need to be returned to n-2 students. How many ways are there to do that? There's n-2 factorial ways. This is divided by the n factorial, and that's that. Similarly, 3 wise intersections will be n-3 factorial divided by n factorial, and so on. Finally, the last step, the intersection of all of these events, all n of them, is again the ratio. The numerator would be the number of ways to return the n exams to n students so that every single student gets their own exam. How many ways are there to do that? One. There's only one way to return all exams in which everyone has their own. Now we're ready to put this in the inclusion-exclusion principle, which for convenience we'll move over here. The probability of E, the union, is the sum of n terms, each of which equals 1 over n, minus the sum of n choose 2 terms, each of which equals this, plus the sum of n choose 3 terms, each of which equals this, and so on. The last term here equals this, 1 over n. Let's simplify. Remember the definition of the binomial coefficient. It's n factorial divided by 2 factorial, n minus 2 factorial. Similarly, this is n factorial, 3 factorial, n minus 3 factorial, and so on. And then something beautiful happens. N minus 2 factorial in the denominator cancels n minus 2 factorial in the numerator. N factorial in the numerator cancels n factorial in the denominator. And what remains from this term is just 2 factorial in the denominator. Similarly here, n factorial cancels with n factorial, n minus 3 factorial cancels with this. And of course, in the first term, n cancels with n. So all in all, this probability is 1 minus 1 over 2 factorial plus 1 over 3 factorial, and so on and so forth. And the last term is this. Remember, this was the complement to the original probability. The original probability, the probability of a derangement that no one has their own exam, is 1 minus that. 1 minus this sum, and that is 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial, and so on. And the last term flips the sign. So instead of writing n plus 1, up here, just write n. That flips the sign, divided by n factorial. You may recognize this partial sum. The Taylor series for the exponential function e to the x. That is the sum of x to the n divided by n factorial. In particular, if you let x to be minus 1, we get e to the minus 1, which is 1 over e, equals the sum minus 1 to the n over n factorial. 1 minus 1 over 1 factorial, which is 1 plus 1 over 2 factorial minus 1 over 3 factorial, and so on. This cancels, and we get this. Except in the Taylor series, the sum continues past n, but it converges to 1 over e. For large n, it becomes closer and closer to that value, 1 over e, which is 0.37 approximately. So for a large class, the probability of a derangement that no one gets their own exam is about 0.37. What's interesting is that if the class gets larger, the probability is not making it more likely or more unlikely. It stabilizes around the same number, 0.37. we solved a non-trivial probability problem, a famous one, the probability of a derangement. Thank you, and stay with me for the next episodes.